First things first, angle of reflection, angle of incidence, all this good business. All right. So if you have a light ray incident on some surface, it'll bounce off, and the angle of incidence, theta I, will be equal to the angle of reflection. Importantly, these angles are measured relative to the normal, this line here, which is just another word for perpendicular. So it's the line perpendicular to the surface. This law of reflection, that the incident angle equals the reflected angle, is the basis for mirrors. And we have a couple of different types of mirrors. The simplest type is the plane mirror, which is just a flat reflective surface. And, well, how do these work? Let's consider our object here, which is this dot. Let's consider a light ray coming off of our object. Let's say it hits the mirror like that. We know the angle of reflection has to be equal to the angle of incidence as measured with respect to the normal. Let's go ahead and draw in our normal. Let's try our best to make theta r match that. That's not great. That looks a lot better. Okay. And so there's your theta r. These two are equal. And this light ray happily goes off like this. Okay, what about some other light rays? What do they do? Well, let's consider the one that basically hits the mirror like that. Well, in that case, the law of reflection is like super easy because it comes in at 90, or sorry, it comes in at 0, right? Because the angle relative to the normal is 0. And so it leaves at 0. And so it retraces itself. And it goes off happily like this. But there's a bit of a problem. These light rays are going like in totally different places. This guy and this guy. They're never going to meet. So how do we get an image in a plane mirror? Well, the answer is we get a virtual image. So let's trace these light rays back. And when we trace back, doing this like sort of hypothetical as if procedure, we use dotted lines usually. So this light ray looks like it came from here. And this one looks like it came from here. Ah, there you go. There's our image. So this is what's called a virtual image. If you try to project a virtual image onto a screen, it would not work. A piece of film, a sheet of paper, it wouldn't work because it's not actually there. The light rays are not converging there. It just looks to our eye as if light rays are emanating from that point geometrically. And that's in contrast to a real image, where you could project a real image onto a screen, and that's because the light rays are actually converging at the point of formation of a real image. But for a plane mirror, the image is always virtual. Always form virtual images. And the other important thing to note about a plane mirror is that the distance of the object in front of the mirror is the same as the distance of the virtual image behind the mirror. And so is the size. But you will have left-right inversion, which everyone's familiar with, just, from looking into the bathroom mirror. So these are the sort of mirrors you have in your bathroom, on the dresser, things like that. Okay. So now that's plane mirrors. We also have spherical mirrors or curved mirrors. And these are basically domes or caps or cutouts of a sphere. And some important terminology. We'll often use C for the center of curvature. We'll use R for the radius of curvature. Curvature. And these are related in a very simple way. The center of curvature, let me just write C. C is the point that is the radius of curvature away from the vertex of the mirror along the optical, sometimes called the principal axis. What does that mean? We'll see in a second. Okay, so with spherical mirrors, we have two types. We have concave, which looks like this, and we have convex, which is already there. So the way to remember a concave mirror is it looks like a cave. And this is how you know that physicists don't really go outside because that does not look like a cave. And a convex mirror looks like it's flexing away from you. And that's how you know that most physicists are not checked. So concave mirrors are also called converging mirrors. Convex mirrors are also called diverging mirrors. They are mirror images of one another, happily enough. And so we can see these terms earlier. You can extend this so that it makes up a whole circle. Then your center of curvature is here. Radius of curvature is like that. Beautiful. Okay. So before we get on to sort of problem solving with mirrors, these ray diagrams and these equations and stuff, it's very important that we get our sign conventions straight. Because people have differing ones, and if we're not consistent, then everything gets messed up. So we have these four quantities of interest. dO is the object distance. So this is the perpendicular distance along the optical axis of your object from the mirror. dI, the image distance, is the perpendicular distance of the image along the optical axis from your mirror. R is the radius of curvature, as before. F is your focal length, which is like the characteristic, all-important parameter for your mirror. And for a spherical mirror, it's related to the radius of curvature in a very simple way. It's just half of the radius of curvature. Okay, so what does it mean when the object distance is positive? Well, you'll almost never see that not happening. Um, as in this is never happens. Never have a negative object distance. When you have a positive object distance, the logical thing happens. Your object is in front of the mirror. And so if it were to happen that you had a negative object distance, that would mean your object is behind the mirror, but you never do that in practice. If your image distance is positive, that means your image is in front of the mirror. This makes it a real image in the sense that we talked about earlier. You can project it onto a screen. And if your image distance is negative, which very well can happen, unlike the object distance, the image distance can very well be negative. This means your image is behind the mirror. And this corresponds to a virtual image in the sense that you can't project it onto a screen. If the radius of curvature is positive, by convention, that's a concave or converging mirror. If it's negative, by convention, that's a convex/diverging mirror. And since we have this very simple relationship between the focal length and the radius, f equals r over 2, these same things apply for the focal length as for the radius of curvature, so I won't rewrite them. Okay, so that's our first key equation, that f equals r over 2. Another very important equation is that 1 over the object distance plus 1 over the image distance equals 1 over the focal length. And since the focal length is equal to half your radius of curvature, right, this is 1 2, and that's 2 over r. So you can write it in terms of the radius of curvature as well. And then our last key equation deals with the magnification. So this is how much your image is blown up. And this is equal to the negative of the image distance over the object distance. So I left a row in the table here. So we can discuss the sign of magnification. Magnification. When magnification is positive, your image is upright. And when it's negative, your image is inverted. So hopefully this table is helpful. Okay. Okay, so with all that background out of the way, we can finally get to drawing some ray diagrams. These are super useful. They're a little bit annoying because of how precise you have to be. Um, but they're good for getting an idea of what's going on geometrically. And then you can verify that with use of this equation, usually. Okay, so here I have a couple of different situations. I have a concave or converging mirror, and I have my object, which is this arrow. And I'm placing the arrow at various distances. So in my first case, I have it outside of the focal length. And I want to find out where its image forms, what its image looks like, and so on. So the way we do that is we shoot some rays of light off of the arrow. We propagate them and we see where they end up. And there's three rays that we really care about. The first one is the one that leaves parallel to the optical axis. So like that. And what's the fate of this ray? Well, it's going to come back and travel through the focal point like that. The second ray we care about is the one that goes through the focal point at first, so like that. And then that one comes off the mirror parallel to the optical axis. So like this. Let me just extend the previous one. And the third ray we care about, and we don't really need all three, but the third ray we care about is the one that goes directly through the center of curvature. In that case, you have this very simple bouncing. You see all the light rays kind of meet here. And so what you have your image forms like so. So it's magnified, it's blown up, it's inverted, and it's real. And those three rays tell you everything you need to know. So let's do it again. This time we'll put the um, object at the focal length, at the focal point. And so again, first ray leaves parallel, comes back through the focal point. Second ray, we want to send it through the focal point, but that doesn't really make any sense. So let's forget about that one. Let's skip straight to the third ray. It'll bounce off and it'll come in the expected way. And oh no, what's happening here? These guys are not converging and they won't converge. These guys are parallel. So usually what we do is we say, okay, let's see what happens on the other side of the mirror. And we trace them back like we did with the plane mirror. But these guys are definitely not meeting over there either. So what's going on here is we don't actually have an image. And the reason for that, beyond these light rays never meeting, I guess philosophically it's not right to say this is the reason for it, but you can see it by using our equation. So here what we're doing is we're setting the object distance to the focal length. So this first term becomes 1 over the focal length plus 1 over the image distance equals 1 over the focal length. In order that this be true, this has to be 0. In order for that to be 0, well, di has to be infinity, right? Because 1 over infinity is 0. And so the image forms all the way out at infinity, which we won't be getting to anytime soon. Last case is we have the object being inside of the focal length. And, again, it's the same exact procedure. So let's do it. First ray we send parallel. it comes back through the focal point, like so. Second ray, we want to send to the focal point, and we want it to come back parallel. But that's a little bit hard because now the arrow is inside the focal length. So what do we do? Well, it's not a big deal. We basically pretend like the ray came from the focal point, and sorry, just a second here. Sorry, did I check something? Okay, and we have this coming off parallel. So what I mean by pretend that this came from the focal point is you can see that the points on this ray are collinear with the focal point. And so that one comes off parallel. And so we have that same sort of problem again, where the rays are going off and they're not really meeting each other. And also let's draw the third ray for good measure, which is the one that bounces off the center of the mirror. To this. So what do we do about this? Well, we'll do the same trick we did with the plane mirror, and we'll trace these guys back. So you must have come from there. You must have come from here. You must have come from here. Okay, that one is just really poorly drawn. So do me a favor and just pretend like this third ray doesn't exist. Okay, yeah, those angles are definitely wrong. The point is that the light rays meet here, and so that's where your image is going to be. Okay. Yeah, so I put this question here. What happens if we place the arrow precisely at the center? And the reason I put it as a question instead of doing it myself is because I got lazy. But what happens is that your image is formed exactly where your object is, except that it's inverted. The way to see that is to apply this directly. So if I place the object, well, let's write it like this. I place the object at the radius of curvature, away from the mirror. I know that 1 over r is 1 over 2 times the focal length because the radius is twice the focal length. And so that means that the focal length, by some easy algebra, is 1 over 2f. But that's the same as the object distance. And so what do you have? You have that the object distance equals the image distance. You have the magnification. It's 1 over 2f. But remember this negative sign, and that's -1. So if your original arrow looked like this, if you put it at the center of curvature, the image will look like this. Okay. Point is, you can work that out with a ray diagram. So I'm just going to go ahead and erase that. But I got to cut that part out. We move on to discussing the ray diagram for the convex or diverging mirror. Don't worry, you don't miss anything. We're going to restart it. So just a bit of a discontinuity, but nothing to worry about. Sorry about that. Okay, where were we? Again, well, let me just restart on this whole convex mirror because I was a little distracted. Okay. So what's going on? We have the ray that's parallel to the axis. That one reflects back through the focal point. The focal point is on the other side. And so that one comes off like this. Next one, the ray that's through the focal point. This one reflects back parallel to the axis. So, ta-dum, ta-dum, ta-dum. And then you have the ray that's to the center of the mirror, and that one reflects back at the same angle relative to the normal. I'm not going to draw it because it'll make things cluttered, but you can see already that the image is forming here. And the nice thing with the convex mirrors is that you don't have to deal with all these cases separately like we did for the concave mirrors. The image is always going to be virtual, upright, and diminished. And again, you can put in that third ray for peace of mind, but I think it's just going to make it too cluttered. But yeah, so the three rays you care about, I'll just recap here. Rays we care about. The first one, parallel to axis. This one comes back through the focal point. The second one is like the dual of that, which is the ray through the focal point. This one comes back parallel to the axis. The third one is the one that goes to the center of the mirror. This one comes back at the same angle. Okay. Let's give this a nice little border. And this is true for both concave and convex mirrors. Okay, so that's all we care about with mirrors. Lenses are very similar. Before we start talking about lenses, though, we'll talk about refraction. And, this is just the phenomenon of light bending. When it goes from one medium to another, it's a result of the change in speed due to the different optical densities of the media. And so, you have this classic illustration of it where you have, let's say this is light, a light ray inside of water. It comes out from the water, goes into the air, and it bends away from the normal. Now, it's not quite this dramatic, but this is sort of what's going on. So that's theta 1, that's theta 2, N1 and N2 are the respective indices of refraction. And you know that this process is governed by Snell's law. So this is like, you put a pencil in water and it isn't really where it looks like it is. That's because of this refraction. Now, the same way reflection is the working principle for mirrors, refraction is the working principle for lenses. And I mean, it's a little bit interesting. It's a little bit more complicated, I should say, because you have two refractions with a lens, because a lens is two surfaces glued together. So you have a first refraction when you go from air into the lens, and then you have a second refraction when you go from the lens into the air. If your lens isn't thin, these don't need to be the same. But in the thin lens approximation, we basically say that these two refractions offset each other, which is to say, don't worry about what happens inside. Okay, so like with mirrors, we have converging and diverging types, although it's a little bit different here. So with a converging lens, those look like sort of teardrops. They're thicker in the center. Thicker in the center. And these are convex lenses. So remember, converging mirrors were concave. Converging lenses are convex. And so an example of a converging lens, when would you need a converging lens? These are for people who are, for example, far-sighted. farsighted. Diverging lens, sort of bowed out. These are thinner in the center. And now be careful, the diverging lenses are concave lenses. And these are useful for people with nearsightedness. Myopia, this one's called hyperopia. Okay, and so as we did for um, the mirrors, let's make some sign conventions here for the lenses. They're a little bit different, but same spirit. So these quantities, they mean the same thing. So this is the object distance. This is the image distance. This is the radius of curvature. This is the focal length. This is the magnification. So remember, the focal length is the point at which the image would form if the light rays came in from infinity, which they don't in practice because we don't have infinite distances. But what that means geometrically is that if the light rays come into the lens parallel, the focal length is the distance away from the lens at which the light rays would form the image. Okay, so let's go ahead and go through this table. So if the object distance is positive, then the object is on the same side of the lens as the light source. Now you don't really have a negative object distance as before, so I'll just say never happens. But if it did happen, it would mean that the object is on the opposite side of the lens um, from the light source. Now here's where the difference is. When the image distance is positive, the image is on the opposite side of the lens from the light source. Remember, for the mirror, it was the same side, but that's because mirrors work on reflection and lenses work on refraction. That's why there's this difference. And so now, if the image distance is negative, that means that the image is on the same side of the lens as the light source. So this corresponds to a virtual image, and before positive object distance, image distance corresponds to a real image. Now a positive radius of curvature is a convex lens converging. I'll write it like this. Converging or convex. And negative radius of curvature is a diverging lens or a concave lens. And notice this is also flipped relative to the mirrors, and that a concave mirror had a positive radius of curvature before. Focal length is going to follow the radius of curvature as before. So I'm not going to rewrite that. And magnification, same deal. If it's positive, image is upright. And if it's negative, your image is inverted. Okay. Now, the really nice thing is that the same equations that held for mirrors also hold for lenses. As long as we use the appropriate sign conventions, we don't have to memorize extra things. We can just use what we already know, as long as we use the right sign conventions. Um, so uh, as before, boom, done. Right, so the key point, the mirrors versus the lenses. Look in this row of the table and look in this row of the table. Okay, so not like we did earlier, what we're going to do now is go through some ray diagrams. And again, these are really great at getting a sense of, are really great for getting a sense of what's going on, but they're super frustrating. And, in practice, you're going to hope you can use the equations, but it really is valuable to see what's going on here. So let's start with the converging lenses, which remember are convex. So what's happening here? Okay, so we put our object uh, at a distance of 2f, and that's sort of arbitrary. Point is that it's sort of outside the focal length. And what's going to happen? Well, the cool thing is that these work basically the same way as the mirrors in terms of what rays we care about. So the first ray we care about is the one that comes in parallel. What happens to this guy? It gets refracted through the focal point. Yeah, like so. Very good. Okay. Now, what's the next ray we care about? That's the one that comes in through the focal point and comes out parallel. So, and a lens has two focal points, right? Because it's two surfaces as opposed to the mirror. And now this one comes out parallel. And then there is, as before, our third ray of interest, which is the one that goes directly through the center, which looks more like that. Beautiful. And so all these guys are meeting here. And so there's your image. Now, same game, except this time we're going to move the arrow, the object, inside the focal length. So how does this one work? Well, nothing changes. Parallel, send it in parallel. It comes out where? Comes out through the focal point. Send the next one in through the focal point. What's going to happen? It'll come out parallel. Except this time we have to be a little bit more careful because now we're inside the focal point, so we have to account for that. How do we account for that? Well, the same way as we did earlier, the mirrors. We sort of send the ray in like that, and it comes out like so. And you can see that this is collinear with the focal point. Okay, and then the last guy goes to the center and gets refracted nowhere. Just keeps on going as before. All right. Okay, so we have our problem. These guys are not meeting. What do? We backtrack. Backtrack you. Backtrack you. And we backtrack you too. And there is our image. Very good. And so that's what's going on for converging lenses. We're going to take a look now at the diverging lens, the ray diagram for the diverging lenses. So what's going on here? Well, let's go with our trusty three rays. First one we send in parallel to the optical axis. If I can draw parallel. And what does that one do? Well, a diverging lens is a little bit different, right? So what we might be inclined to do is to send it through the focal point like that. But that wouldn't be a diverging lens, that would be a converging lens. However, we still do want it to pass through the focal point. That's a good thing because we have two focal points. So basically what happens here is the light comes in and it gets refracted off like this. But notice, we can back trace this, and it is indeed collinear with the focal point. Our next ray is going to be the one we send in through the focus, and that leaves parallel. So again, we need to be a little bit careful because this is a diverging lens, so we don't want to fall into the natural tendencies we have. I guess that might be a bit of an overstatement, but we don't want to do the same thing we did with the converging lens. So here in comes this ray here, come out, and it'll come out parallel because of this collinearity with the focal point there. And then we'll send our trusty friend through the center, and he's unaffected. He just passes straight through. So now the game is back propagation. We already back propagated this guy. Now we need to back propagate this guy. So there you go. All of these guys meet here. And so there's your virtual image right there. And that's how it's going to be for the diverging lenses. You know, wherever you move the object, the size will change, but that ray tracing procedure will be pretty much unaltered. Okay, so now, because this is the mcat, um, we'll do some medical applications of this. I guess I sort of already mentioned this up here, um, but if you're farsighted, which is down here, farsighted, this is hyperopia. Well, what that means is that your retina is ahead of where the light rays are being focused by the converging lens in your eye. So you want the focusing to be happening here, but it's happening back here. How do you fix that? Well, you put in a converging lens to basically make it happen earlier against the retina. The other thing we can have is myopia, which is nearsightedness. And here what's happening is that the converging lens in your eye is focusing the light rays way too early. The retina is all the way back here. How do you fix that? Well, you push them apart so that the converging happens later, and you do that by installing a diverging lens. Now, of course, the eye is very complex, and if you need to correct for both of these to some extent, then you use bifocal glasses. Correct both simultaneously. Use bifocal glasses. Right. And so there's our medical application. So that's most of the main stuff, right? The initial question was about converging and diverging lenses and mirrors, and hopefully we've covered that to your satisfaction. But there are a couple of other things to know about geometric optics as well. So this whole time we've been working with the thin lens approximation. When it fails, we have to use something called the lens maker's equation, which is right here. This n is the index of refraction of the lens material, and R1 and R2 are the radii of curvature of the surface of lens 1 and lens 2 respectively. And so this you need when the lens thickness is not negligible. Oftentimes we'll characterize a lens by its power. So that's just 1 over the focal length. The units of this, if you measure the focal length in meters or inverse meters, opticians like to call these diopters. The power of the eye is like 60 diopters or something, for reference. If you have a bunch of thin lenses that are sort of back to back in contact with each other, their power is going to be the sum of the individual powers. So the effective power is just going to be the sum of power one and two and three and four. Alternatively, you can say that the equivalent focal length is the sum of the inverse focal lengths. Or I'm sorry, you can say that the inverse of the equivalent focal length is the sum of the inverse focal lengths, right? Because power is 1 over the focal length. If your lenses are not in contact, and so this is what happens when the image from one lens is the object for another. So this is like a telescope or a microscope or something like that. Well, then what happens is that the magnifications multiply. I've used this pi symbol for multiplication here because I felt like an asshole. But this just means M1 times M2 times M3 and so on. Whatever makes up your compound lens system. Um, Other things to know, spherical aberration. This is basically smudging, blurring, so you don't have all your rays coming to focus at the same focal point. You have some circle of confusion here, and so you get a blurry image around the edges. An aberration is some kind of imperfection. We also have chromatic aberration, which is basically wavelength dependent aberration. So effectively what happens is because of this phenomenon called dispersion, where the index of refraction depends on the wavelength, different wavelengths of light or different colors of light get focused at different points. And so this is really cool. This is what sort of gives rise to colored rings around objects. Those blurry sort of colored rings you see. Oh, and don't forget about total internal reflection, which is actually a refraction phenomenon. I don't feel like doing it, but if you have questions, feel free to ask. And that's it.